everybody. Namaste and welcome to yet one more video from Murali's World of Physics. Today's video is something particularly special as far as I am concerned. It happens to be the 25th video from Murali's World of Physics. And therefore, I had decided that the topic of this video also should be something special. Recently, I had been on a trip to Sydney in Australia, visiting my son and family. There, I had the occasion to visit the paddies markets, which is very famous in that locality in central Sydney. There were several souvenir shops in that market, and among many other items like souvenirs and a memento ranging from keychains, fridge magnets and other types of the most appealing item as far as I was concerned was the boomerang. I decided that before leaving Australia I will purchase one boomerang as a souvenir from one of those shops. A few days after that, one of my cousins who is living near Sydney had visited us, and to my surprise and thrill, he gifted me with a boomerang. At the time, he suggested that I do a YouTube video dealing with the physics of boomerang. So this particular video is a result of his prompting. What is a boomerang? Well, a boomerang is a weapon traditionally used in war and hunting by the aboriginals of Australia. These were earlier known as the Burgan or Baragadan in the local language. These have been traditionally well known for their characteristic property of returning to the thrower. Colloquially, the term boomerang is often used metaphorically to describe a situation where an action or statement comes back to have unexpected negative consequence for the person who initiated it. This usage is derived from the boomerang's characteristic of returning to the thrower. However, all boomerangs are not of the returning type. Many are of the non-returning type. The non-returning boomerang is longer, straighter and heavier than the returning variety. With it, animals were maimed and killed, while in warfare, it caused serious injuries and death to the opponents. Although used primarily for leisure and recreation, returning boomerangs are also used to decoy birds of prey thrown above the long grass to frighten game birds into flight and into waiting nets. Returning boomerangs are lightweight and have a special curved shape. A returning boomerang flies in a circle and comes back to the thrower. People use returning boomerangs for sporting events and as toys. These usually have a V shape and is designed to return to the thrower, of course. Usually it's about 16 to 20 inches long, that is about 35 to 45 centimeters long. One particularly curious application of the boomerang was shown in the film How to Steal a Million. Here the thief uses a boomerang to set off the alarm system that protects a costly and unique sculpture, bringing the museum guards and police. Finding nobody there, they return to their positions. The same thing happens on 2 more occasions, and finally, frustrated, they switch off the alarm, after which the thief coolly collects the sculpture and go away. The vital boomerang attributes are convex top surface, distinctive curve, thin body and a wide surface area, and these are essential to the boomerang's aerodynamic properties. The returning boomerang has specialized components that make it behave a little differently than an ordinary bend stick. A classic banana-shaped boomerang is simply 2 wings joined together in a single unit. This is the key to its odd flight path. The boomerangs come in various shapes and sizes. So this is one particular shape, this is another type. Now this has 3 wings, this also has 3 wings and this has 4 wings. Of course, the uses may also depend on the shape and size. The different shapes encountered are symmetrical boomerang, asymmetrical boomerang, beaked or hooked boomerang and cross boomerang. These are used to hunt kangaroo and emu in the Australian plains, and they are also useful for digging and in ceremonies. They have also been used in sports and recreational purposes. In addition to the elementary physics concepts of forces, velocity and acceleration, linear momentum and kinetic and potential energies, as in the case of the aircraft in our earlier video on air pockets, we come across the following additional concepts: torque and moment of inertia, angular velocity and acceleration, rotational energy, gyroscopic and precessional motions, etc. All these refer to rotational motion or speed as it is otherwise known. In rotational motion, torque is equivalent to force in linear motion, and the moment of inertia is equivalent to the mass of the object. Angular velocity and angular acceleration replace linear velocity and linear acceleration respectively, and rotational energy replaces kinetic energy. So this gives the main concepts regarding rotational motion. So we have a particle of mass m moving in a circular orbit of radius r. So it moves at constant distance from the center of the circle. Now this arrow shows the axis of rotation of the mass at this fixed distance r. Obviously, from Newton's first law, since the object is not moving in a straight line with uniform velocity, there should be a force acting on the object. The speed of the particle does not change. Only the direction changes. That means the velocity changes, but the magnitude of the velocity remains constant. So it obviously means that there cannot be a force along the trajectory. So the force should be normal to the velocity at every point on the trajectory. So the force is towards the center. So it is called the centripetal force. So as a result, the particle moves with constant velocity along the circumference of the circle of radius r. So with reference to some fixed set of axes, the angle made by the radius vector changes with time. That means the angle theta changes with respect to time. So there is a particular velocity of this change, and since a force is acting, then from Newton's second law there should be a corresponding acceleration also. So we have the angular velocity omega is equal to d theta by dt, and the angular acceleration alpha is equal to d omega by dt. So omega is the angular velocity, alpha the angular acceleration, and in this case of this rotational motion, it is not the mass alone which comes into the picture in terms of deciding the effect of the force on the object as evidenced by the Newton's second law. So in Newton's second law we have F is equal to ma, where a is the linear acceleration, and correspondingly we have a quantity called the torque replacing force, and of course this is the acceleration, and the corresponding quantity is I, which is equal to mr square, which is known as the moment of inertia, and the equivalent quantity of force is the torque, tau. So tau is equal to I alpha and I is equal to mr square. The angular momentum is defined as the product of the moment of inertia and the angular velocity. So just as we have linear momentum, P is equal to m into v. Just as force results in acceleration along the force direction directly proportional to the magnitude of the force and inversely proportional to the mass of the object as per Newton's second law, and there results a change in the velocity as a result of this acceleration. Similarly, in rotational motion, a torque produces angular acceleration which is directly proportional to the torque and inversely proportional to the moment of inertia. Now it is obvious that a single force acting at a point cannot cause rotation, obviously, because that will lead to a linear motion only. So therefore, two forces separated by a distance between their lines of action is necessary for rotation. A pair of such equal and opposite forces with non-coinciding lines of action which produce rotation is called a couple. So we have a couple acting on a body. So we have one force F, another force of equal magnitude F, but acting in the opposite direction, and their lines of action are separated by a distance r. So this combination of two forces is known as a couple. Now if you form a vector tau, which is the cross product of the radius vector and the force vector, so tau is equal to r cross f. So this is the torque. So that is actually The magnitude of torque is the magnitude of each force multiplied by the perpendicular distance between their directions of action. In linear motion, we have F is equal to ma, so this has to be replaced in rotational motion by tau is equal to I alpha. The moment of inertia, as I have already mentioned, is defined as I is equal to mr squared. So here m is the mass of the body which is rotating at a distance r from the rotation axis. The moment of inertia plays a crucial role in determining how effective an object is in rotating. So it is a measure of an object's resistance to changes in its rotational motion around a specific axis. So obviously, this will depend on the mass distribution of the object relative to the axis of rotation. In the case of an extended object where there is a distribution of mass with respect to the given axis, then the simple expression for the moment of inertia has to be replaced by an integral of the quantity dm into r square over the entire mass distribution, where dm is a small mass element at a given distance r from the axis. Now, angular momentum is equivalent to linear momentum in linear motion, and it is defined as L is equal to R cross P. In the case of circular motion, omega is equal to V by R and L is equal to M omega R square. So this can be obtained simply from our earlier expressions and combining those with L is equal to R cross P. So in linear motion, we have the momentum is equal to mv, which is this P. By differentiating the expression for the angular momentum with respect to time, one arrives at the following: dl by dt is equal to d by dt of r cross p, and since r is a constant in circular motion, we can take this outside, and m is also a constant, so that also can be taken out. So we have rm with the, so r is a vector here, r cross d by dt of v. So that is equal to r cross f, since d by dt of the momentum is the force. So r cross f, and that is the torque. The wings of the boomerang are set at a slight tilt and they have an aerofoil design. They are rounded on one side and flat on the other, just like an airplane wing. As I had explained in my earlier video on air pockets and effects on airlines, we see that this design gives a wing lift. So this is our aerofoil. This we had seen in our earlier video on air pockets. So the air rushes past the aerofoil in this direction. So there is a velocity of the air molecules on the top surface. There is a velocity of air molecules on the lower surface. And it happens that the velocity on the lower side will be low as compared to the velocity on the upper side of the aerofoil. And this results in a difference of pressure. There is a high pressure on the lower side and there is a low pressure on the upper side. And this results from partly from the low curvature on the lower surface and the higher curvature on the upper surface, which results in longer distance of movement by the air molecules on the upper surface and shorter distance of travel on the lower side surface. And that is why there is a difference in velocity. So the air particles move more quickly over the top of the wing than they do along the bottom of the wing, which creates a difference in their air pressure. So the aircraft wing has lift when it moves because there is a greater pressure below it than above it. And the basic physics principle here is the Bernoulli's principle. This can be derived from the principle of conservation of energy, which requires that the sum of the kinetic energy, potential energy and the internal energy of the system remains a constant. So we have P1 plus half rho V1 square plus rho g Y1 is equal to P2 plus half rho V2 square plus rho g Y2, where P1 and P2 are the two pressures, half rho V1 squared, this is the kinetic energy per unit volume, rho is the density of the air, and V1 is the velocity on the one side and V2 is the corresponding velocity on the other side, and the Y1 and the Y2 are the heights of the 2 points at which the pressures are P1 and P2 above a particular reference surface. And G is of course the acceleration due to gravity. So we have P1 by rho G plus half V1 square by G plus Y1 is equal to P2 by rho G plus half V2 square by G plus Y2. This we get by dividing this first equation by rho G. In other words, we can restate this statement as the pressure head plus velocity head plus potential head. So the sum of these three quantities should be equal at every point in the air volume. Now we call this a head. Each term is known as a head because it has the dimensions of a distance or height. So therefore, the origin of the lift on the aerofoil is because of the velocity difference, which leads to a pressure difference on the two sides of the aerofoil, the lower surface and the upper surface. So this differential pressure results in unbalanced force from high pressure side to the low pressure side. So the direction of this force is from the high pressure side, which is on the lower surface of the aerofoil, to the low pressure side, which occurs on the upper surface of the aerofoil. And this is precisely what happens in the case of the boomerang also as in the case of the aeroplane. Now theoretically, the lift force experienced by the blade of the boomerang can be obtained as given by following expression. The lift force Fl is equal to half rho V square Cl into A. Of course, rho is the density, V is the relative velocity, Cl is the lift coefficient. This is a particular coefficient characteristic of the air volume and the aerofoil, and A is the area of the wing. The two wings of the boomerang are arranged so that the leading edges are facing in the same direction, like that in the blades of a propeller. At its heart, in fact, a boomerang is just a propeller that isn't attached to anything. It's on its own. Propellers like the ones on the front of an airplane or on the top of a helicopter create a forward force by spinning the blades, which are just like wings, through the air. So this force acts on the axis, the central point of the propeller. A boomerang would therefore simply fly off in one direction as it spun, just as a plane with a spinning propeller will move in one direction. If one holds it horizontally when it is thrown, the forward motion would be up because that is the direction of the axis is pointing. The boomerang would fly up into the sky like a helicopter taking off until it stopped spinning and the gravity pulled it down again. On the other hand, if it is held vertically when it is thrown, the boomerangs would simply fly off into the right or left. That's what should happen from the direction of the lift produced. But obviously, this isn't what happens. The upward lift generated counterbalances the gravitational force that we know. In order that the boomerang maintains its height, then according to Newton's third law, the action and reaction should be equal and opposite. So this keeps the boomerang in air without falling down to the earth. There are actually 5 main forces controlling a boomerang in flight. The first is the lift, which is generated by the aerodynamic shape of the boomerang's wings. And this force acts perpendicular to the direction of motion and helps to keep the boomerang in the air. Second is the drag. This is the resistance force acting opposite to the direction of motion and is due to air friction. This drag slows down the boomerang. Thirdly, of course, we have the gravitational force. This is the downward force due to the weight of the boomerang acting towards the center of the earth. Then we have the important centripetal force, which is the force acting towards the center of the circular path that the boomerang follows. It is also responsible for the curved flight path of a returning boomerang. Finally, we have the important concept of gyroscopic precession. This is in fact a torque effect due to the boomerang's rotation. It causes the boomerang to change its orientation and contributes to the curved flight path. It is really not a force per se, but an effect of the rotating mass of the boomerang. So we see that there are 5 variables involved in a boomerang flight. For a boomerang to actually travel in a circle and come back to its starting point, which is the characteristic property of the boomerang, all of these forces have to be balanced in just the right way. To accomplish this, we need a well-designed boomerang and a correct throw angle. The combined effect of the lift force and the resulting torque causes the boomerang to precess. As the boomerang precesses, the direction of the lift force changes, continuously altering the boomerang's trajectory and results in a curved flight path that can bring the boomerang back to the thrower if the throw angle and initial velocity are chosen properly. A fundamental set of equations governing rotational motion of a rigid body is the so-called Euler's equations. They were formulated by Leonhard Euler in 1736, exactly about 50 years after Isaac Newton formulated his laws of motion for linear motion. The Euler's equations of motion are as follows: I1 omega 1 dot plus I3 minus I2 into omega 2 omega 3 equals to tau 1, and similar two more equations which involve the various components of the physical quantities involved in the motion of the object. Here the i's are the moments of inertia along the principal axis of the boomerang, the omegas are the angular velocity components, and the omega dots are the respective angular accelerations. The taus are the externally applied torque components. Euler's equations are fundamental in explaining and predicting the behavior of rotating bodies and leads to the phenomena of precession and gyroscopic motion. The motion of a boomerang is also affected by the so-called Coriolis force, but the effect is generally quite small and often negligible in typical boomerang throwing conditions. This force is given by Fc is equal to 2m omega cross v, the vector product of omega and v. M is the mass of the object, omega is the angular velocity vector, v is the velocity of the object. Typical calculations lead to a value of about 10 raised to minus 3 meters per second squared, the acceleration in the case of the boomerang. And we can see that this acceleration is very small compared to the typical accelerations which arise from the aerodynamic forces acting on the boomerang. Another important consideration in the case of the boomerang is the precessional motion. This is so much evident in the case of a spinning top and also in the case of the movement of the astronomical objects on their orbits. Precession can be defined as the change in orientation of the rotational axis of a rotating body. If the axis of rotation of an object rotates about a second axis, then the object is said to precess around the second axis. The torque produced due to the spinning top is perpendicular to the angular momentum, of course. Thus, the direction of the torque changes, but its magnitude does not. So, the torque precesses around a vertical axis since the torque is always horizontal and perpendicular to the angular momentum. Here is a description of the spinning top. So, we have the spinning top, its mass is m and the gravitational force mg acts vertically down. L is the angular momentum, this is the axis of rotation of the top. Omega is the angular velocity and I is the moment of inertia. So we have this top spinning in this direction. So let us assume that there is a tilt in the axis through some particular angle. So therefore, because of this tilt, the gravitational force produces a torque which is given by mg multiplied by this perpendicular distance from the vertical axis. So therefore, it is this particular torque which produces a rotation of the axis of the spinning top in this particular direction. So that motion is known as precession. Obviously, if the axis is exactly vertical, then the lines of action of the gravitational force coincides with the axis and the resulting torque in this case will be 0 because x happens to be 0 in this particular case. So therefore, a spinning top whose axis is exactly vertical will not precess. If there is a slight angle tilt of the axis with respect to the vertical, then there is a corresponding gravitational torque and the top starts precessing around this particular axis. Here is a demo of the rotational motion of a spinning top. Now let us first consider the top with a vertical axis. So in this case, since there is no torque, the top keeps on spinning about the vertical axis and there is no precessional motion. Now on the other hand, suppose the axis of the top is tilted at an angle with respect to the vertical, then it is seen that the axis of the top itself rotates about the vertical direction. So the tip of the top traces out a circle, and this process is known as the precession of the spinning top. The precessional velocity omega p can be calculated by the equation omega p is equal to tau by I omega, where tau is the torque, I is the moment of inertia, and omega is the angular frequency of spinning. In the case of a typical spinning top, if we substitute some typical values of the parameters, for example, mass 100 grams, that is 0.1 kilogram, the distance from pivot to center of mass r is equal to 0.1 meter. Of course, the gravitational acceleration g is 9.81 meter per second square, and suppose the moment of inertia of the top is 0.001 kilogram meter square with respect to its axis, and the top is spinning with an angular velocity omega is equal to 10 radians per second. That's typically about 1.5 rotations per second. So if you substitute these values into the previous expression, we get a value of 9.81 radians per second for the precessional frequency. Another well-known example of precessional motion is the rotation of the Earth. The gravitational forces exerted by the Sun and the Moon on the Earth create a torque on the Earth's equatorial bulge. What is the bulge? This is the slight bulge around the equator due to the Earth's rotation. And this causes the Earth's axis of rotation to slowly trace out a conical shape over a period of approximately 26,000 years. This movement is what we refer to as precession of the Earth's axis. Both the Moon and the Sun influence this particular phenomenon. Now, the lunar influence, the Moon is the primary contributor to the precession of the Earth's axis because it happens to be closer to the Earth than the Sun, and therefore exerts a stronger gravitational force compared to the Sun. The solar influence, although much less as compared to that of the Moon, the Sun also contributes to the precession due to its gravitational pull on the Earth's equatorial bulge region. So this is a pictorial representation of the precessional motion. This is our Earth. This is the rotational axis about which the Earth rotates. Then this is the orbital plane in which the rotation takes place. This is the vertical direction passing through the center of the Earth. And of course the gravitational pull is in the direction shown here. And this is the gravitational bulge that I have just talked about. So when the Earth rotates about its axis once in every 24 hours, the gravitational force due to the Moon and the Sun acting through the center produces a gravitational torque which is acting in this direction, and therefore the tip of the axis traces out an imaginary circle in space. So this is known as the precessional circle. Now what are the effects of precession? The precession of the Earth's axis affects the orientation of the Earth's rotational axis obviously. So we know this is about 23.5 degrees with respect to the stars. It causes a slow change in the position of the celestial poles and the equinoxes. What are these equinoxes? These are the points where the Earth's orbit intersects the celestial sphere. So this phenomenon is responsible for the changing pole star over the millennia. For instance, currently Polaris is the North Star, but due to the precessional process, over a course of time, other stars will become the North Star in the distant future. Now coming back to the boomerang, it follows a curved path and returns to the thrower due to a combination of its aerodynamic design, gyroscopic stability, and the physics of lift and precession. They are typically designed with two or more wings that are asymmetrical in shape and have an aerofoil cross-section. This shape is crucial for generating the lift similar to that in an aeroplane wing. Now when a boomerang is thrown, each of the two wings generates lift. But because of the boomerang's rotation, one wing, which is usually the leading or advancing wing, moves faster through the air than the other, which is the trailing or retreating wing. So this difference in speed causes a difference in lift. The faster moving wing generates more lift and the slower moving wing generates comparatively less lift. So this uneven lift between the wings creates a torque on the rotating boomerang, and this torque causes the boomerang to tilt and rotate its flight path, which is the process of precession. The boomerang spins rapidly around its center of mass, creating gyroscopic stability, and this gyroscopic effect helps to keep the boomerang stable in the air and contributes to its curved flight path. The combination of lift, gyroscopic stability and precession causes the boomerang to follow a curved path. As the boomerang tilts, the direction of the lift force changes, guiding the boomerang in a circular or elliptical path. So that is the basic physics behind the motion of the boomerang. If thrown correctly, the boomerang's curved flight path will eventually bring it back to the thrower. There are several factors which are important in this aspect. The angle of release, the spin and the tilt, that is the angle of attack, all need to be carefully controlled to ensure that the boomerang returns to the thrower. Thanks for watching this video. With this is Professor Muralidhara Warrior signing off from Murali's World of Physics. I'll be back with more interesting videos on physics concepts and principles. Till then, goodbye. If you like this video, kindly click on the like button and share this video with your friends and relatives and in your different groups. If you have not already subscribed to my channel, kindly do it now, and please don't forget to click on the bell icon so that you will get notifications in future regarding my upcoming videos.